Integral as a net change, AP questions. Objectives. By the end of this lesson, you should be able to set up and solve AP net change problems, find and store functions and points of intersection in the graphing calculator, and evaluate integrals involved in net change problems on the graphing calculator. Alright, let's jump into our first AP question. Traffic flow is defined as the rate at which cars pass through an intersection, measured in cars per minute. The traffic flow at a particular intersection is modeled by the function f, defined by f of t equals 82 plus 4 sine of t divided by 2 for times t between 0 and 30. And f of t is measured in cars per minute, and t is measured in minutes. So before we look at the 4 parts of the question we're being asked to answer, let's try to understand this function that I've been given. This function that I've been given represents a rate. It represents a derivative. Even though this notation doesn't have the prime notation or d something dt, this is still a rate of change because of the units of measure are in cars per minute. So if I were to substitute a time, t, in minutes into this t, or into this t in other words, what units would come out are in cars per minute. So just substituting in something like 1 right here, f of 1. So I'd substitute a 1 right here into this t. So 82 plus 4 sine of 1/2 is a numerical value. That numerical value is in cars per minute. So it means that at exactly 1 minute, there are that number of cars per minute passing through that specific intersection, so a particular intersection. So just substituting in values into this t will give me out units in cars per minute. So now let's take a look at the first question. To the nearest whole number, how many cars pass through the intersection over the 30-minute period? So let's go again. To the nearest whole number, how many cars? So my answer has to be in a unit of cars. How many cars pass through the intersection over the entire 30-minute period? So the first thing I want to clarify is we are not just substituting in the number I see here, 30, into the function. So the best way to answer a lot of these questions is to truly understand the units. If I were to just substitute 30 into f of t, my answer would be in cars per minute. But we just agreed I want to know how many cars. So that means that in calculus we have 2 options. We're either going to take the derivative or we're going to evaluate an integral. Now in this case, I want to evaluate an integral. I want to get to just cars. If I were to take a derivative in cars per minute, my answer would be cars per minute, or cars per minute squared if I took the derivative of f of t. But instead, I'm going to evaluate an integral. Now, again, to help us understand the concept of units, let's say we were to graph this function f of t. So for now, let's assume I don't know exactly what it looks like. This is just my function f of t. Now, the units of my function, which means the units on the vertical axis we've said a couple times now, are cars per minute, and the units of my horizontal axis, time, is in minutes. So finding the area under the curve during the first 30 minutes, so from 0 to 30, the area is going to be the units of the base times the units of the height. So cars per minute times minutes, cars per minute times minutes, well, the units that are going to cancel are minutes, and my answer will be in cars. So understanding the units is really going to help us evaluate this first part of the problem. So part A, I'm going to have to set up the integral from t equals 0 to t equals 30. So I wanted to know how many cars pass through over the 30-minute period. So starting at time 0, ending at time 30, of the function f of t dt. Now, since the function has been given to us in the problem, 82 plus 4 sine of t over 2, there's no need to rewrite it. So we're talking about AP problems now, and we want to save ourselves some time. What we do have to write down is the setup of the integral. So this right here is absolutely required. So the integral from 0 to 30 of big F of t dt. So let's talk about a couple things now. I want to make sure that I write big F of t dt, so I don't want to start changing things to little f. There is no little f. There is no x's involved, so I want to be sure to recall the function that is being used in the problem. And now I need the numerical answer. So to find the numerical answer, this particular problem is a graphing calculator problem. So off to the left here you see a TI-84 graphing calculator. So let's go ahead and go over how we would enter this into our graphing calculator. Now, this one function is going to be used throughout the entire problem. We're probably going to have to use it more than once in our calculator, so we're going to go ahead and store it and enter it as y equals. So we can go ahead and turn the calculator on, go to y equals, and enter our function. And you'll see I've already gone ahead and done that. So 82 plus 4 sine of course, x over 2, because we don't have the variable t, but x will do. So here is my function. Now, something else we should troubleshoot right now is that we want to make sure that our calculator is in radian mode. So clicking mode, it is highlighted as radian mode because that will completely make our answer wrong otherwise. So y1 is right there in our calculator. So let's go back to the home screen. So second quit. And now we're evaluating this integral here. So we're going to go ahead and go to math, and we go to math 9. And our lower limit of integration is 0. Our upper limit of integration is 30. And to avoid entering that function in over and over again, we stored it as y1. So we're going to go to vars, go right 1 to yvars. We can hit 1 or enter for function, and then enter again for y1. And then we'll fill in the variable in our differential as an x. And then we can go ahead and hit enter. So the numerical answer is 2,474, and it says to the nearest whole number. So if this was not here, we would definitely go to the thousandths place, but because to the nearest whole number, our answer is 2,474 cars. So we wouldn't want to think of a fraction of a car. So let's go ahead and fill in our answer. So 2,474 cars is our numerical answer. So this is what we would need to write in order to obtain full credit on this problem. We'd have to set up the integral, but again, there's no need to write out the whole function. So 82 plus 4 sine t over 2, we can just call it what it was named, big F of t. And then we do have to write our numerical answer. And again, we were told to the nearest whole number, so no need to round or truncate to the thousandths place. Alright, so now let's move on to part B. Part B is asking, is the traffic flow increasing or decreasing at time t equals 7? Give a reason for your answer. So here is the traffic flow. Well, traffic flow had a name or a function. The function is called f of t. So here they've written it out in words. Is the traffic flow increasing or decreasing? But traffic flow is really can be thought of as f of t. So this problem is asking us, is the function, is f of t increasing or decreasing at time t equals 7? So now this takes us back to remembering that a function is increasing when its derivative is positive. So we're looking at the specific value right here at t equals 7. So for part B, we need to determine the sign, positive or negative, of f prime of 7. So is the traffic flow, which was called the function f of t, is f of t increasing or decreasing at time 7? We're really asking ourselves, is the derivative positive or negative at time t equals 7? And because this is a graphing calculator problem, again, we can do this on the calculator, and we've already stored the function big F as y1. So now we're doing a derivative, a numerical derivative. We can go to math 8, and our variable is x, and we want to go to vars, over to yvars, enter, and use y1 again. And we're evaluating this particular function at a specific value at 7. So since the answer is negative 1.7829, we know that f prime of 7 is a negative value, so if the derivative is negative at a particular value, the original function is decreasing. So we can say f prime of 7 equals negative 1.872, which is less than 0. So there is my reason. So f is decreasing. Or we could replace f with traffic flow, as that is what the function f represented, and that was the way that the problem was worded. So we'd probably want to put, so the traffic flow is decreasing. So we answered parts A and B of this question, and we'll hold off in a later lesson to go over parts C and D. Alright, moving on to the next AP question. For times t between 0 and 31, the rate of change of the number of mosquitoes on tropical island at time t days is modeled by r of t equals 5 radical t cosine of t over 5 mosquitoes per day. There are 1,000 mosquitoes on tropical island at time t equals 0. So this last sentence here says at the beginning, at time t equals 0, there were 1,000 mosquitoes. But then the rate of change of mosquitoes varies based on this function r of t. So the rate of change of mosquitoes is given by 5 radical t cosine of t over 5. So the units, because this is a rate, are in mosquitoes per day. So even though this is called r of t, I've been given a derivative. I've been given a rate of change, the rate of change of mosquitoes. So now let's look at part A. Show that the number of mosquitoes is increasing at time t equals 6. So I want to show the number of mosquitoes is increasing. So what I would need to show is that the rate of change of the number of mosquitoes is positive. So here's where a lot of students are going to make a mistake, is they're going to think I need to take the derivative of r of t and substitute in 6. Because they understand that to find where a function is increasing, I need to know that its derivative is positive. So at this specific time, I would need to show that the derivative is positive. But this is a derivative. This is a rate of change. It's the rate of change of mosquitoes. So if we want to show that the number of mosquitoes is increasing, I need only plug 6 into r of t and show that r of 6 is positive. So for part A, I need to find r of 6 and show that this quantity or this value is positive. So now going to our graphing calculator, we're going to use this function often, so we're going to store it as y1. This whole problem is a graphing calculator problem. So I've stored it as 5 radical x cosine of x over 5. Again, making sure I'm in radian mode still. When you enter this function, just be careful that the square root function stops with just x underneath it, and then you move to the right and get out of the radical before you put cosine x over 5. So the biggest mistakes are going to happen just entering in the function incorrectly. So now that this function is stored, I need to find r of 6. Well, we just called that function y1. So on the home screen, I'm going to go to vars, yvars, enter to get y1. So what I want is y1 of 6, because we stored r as y1. So this looks exactly like this does because we stored r as y1. So now we can just go ahead and hit enter, and we get out 4.4379, etc. So this is a positive quantity. So r prime of 6 equals 4.437, which is greater than 0. So the number of mosquitoes is increasing. I'll just abbreviate mosquitoes, is increasing. So here the big picture is we don't need to see the prime notation to understand this is a derivative. The fact that this is a rate of change, mosquitoes per day, so this just goes back to the very first topic, the beginning of the year, understanding a quantity versus a rate. So since when substituting in a time here, I get out a rate, mosquitoes per day. This represents a derivative. So it's the rate of change of mosquitoes. So if I want to know whether the number of mosquitoes is increasing at time 6, I need only plug 6 into the rate of change of mosquitoes, which is called R of t. All right, part B. At time t equals 6, is the number of mosquitoes increasing at an increasing rate, or is the number of mosquitoes increasing at a decreasing rate? Give a reason for your answer. Alright, so part B really pushes whether or not you understand, again, the concept of rates. So we just said that even though this has no prime notation, this R of t function is a derivative. It represents a rate of change with the units in mosquitoes per day. So substituting in 6, R of 6 was 4.437, but again, the units would be mosquitoes per day. So on day 6, the rate of change is 4.437 mosquitoes every day. Now, part B is asking, is the number of mosquitoes increasing at an increasing rate? So what that means is, we're trying to figure out if from day to day, the number of mosquitoes, the rate of change of the number of mosquitoes is on its way up or on its way down. So around 6, so on day 5 to day 7, on day 5 was the rate of change, let's say, less, and on day 7 was the rate of change more, so that the rate of change was on its way up, meaning that the rate of change was increasing at an increasing rate. Or maybe on day 6, the rate of change was 4.437, but on day 7, the rate of change was 2.437. So the rate of change is increasing. The number of mosquitoes on the island is still getting bigger, but it's getting bigger at a decreasing rate. So, in other words, from one day to the next, more mosquitoes are still going onto the island, but not as quickly. So either the number of mosquitoes we're adding is going up every day, or the number of mosquitoes we're adding is going down every day. That's the question we're asking. So in order to determine that, we are now going to need the derivative of the derivative. So we are going to need r prime of t's sign, whether that is positive or negative. So for part B, I'm interested in r prime of 6. That's a rate of change of a rate of change. So r prime of 6 is truly a second derivative. So to find r prime of 6, I can go back to my calculator. I still have it stored r as y1. So now I need a derivative. So math 8. And I have d dx of the stored function y1. And I want that evaluated at 6. So since this is a negative quantity, r prime of 6 is negative 1.913, which is less than 0. So the number of mosquitoes is increasing at a decreasing rate. So every day, more mosquitoes are going to be on the island, but the number of mosquitoes added every day is going to be less and less. So on day 7, maybe 4.2 mosquitoes are added, and then on day 8, 4.3 mosquitoes are added. So it's specifically, though, at time t equals 6. So we're interested in what's going on right at this time. So that's why we needed to calculate r prime of 6. So the answer is increasing at a decreasing rate. And that's the reason for my answer. So there's no explanation. The reason is the notation that we wrote down, that r prime of 6 is negative 1.913, which is less than 0. Alright, moving on to part C. According to the model, how many mosquitoes will be on the island at time t equals 31? So after the 31st day, how many mosquitoes will be on the island? Round your answer to the nearest whole number. Alright, so here on this problem, we are going to need to take into account 1,000 mosquitoes, which is how many were on the island to begin with at time 0. So for part C, how many mosquitoes were on the island after 31 days? So 1,000 is where we were to begin with. And now r of t is the rate of change of the number of mosquitoes. at different times t, so I'm going to need to integrate this quantity. So I'm going to add the integral of the rate of change between 0 and 31 days. So between t equals 0 and t equals 31 of r of t dt, this is the net change in the number of mosquitoes. So this is the total net changes in how many were added, how many were subtracted over the whole course of 0 to 31 days. So this is the total net change plus how many there were to begin with. So now this can be evaluated in my graphing calculator. And again, if you don't understand why just outright this represents the net change in the number of mosquitoes, we can always go back to units. So again, just graphing. R of t is some generic function where the units of R of t are the rate mosquitoes per day. After so many days, t, the area, again, the units would cancel. Area is base times height, so mosquitoes per day times days. The units of days cancel to give us just mosquitoes. And my answer, or my question, was asking for how many mosquitoes. So we're plugging this into our calculator. R of t has been stored for a while now, so we're going to do, and if we want, we could jump straight to 1,000. Whoops, let's do that. So let's say 1,000 plus, and then math 9, the integral from 0 to 31, and then our function is y1, and the variable is x. So this up here means it's taking a little bit of time to compute. So our answer is 964. So let's go ahead and write that down as our answer. And again, we were allowed to round our answer to the nearest whole number because there's no such thing as, 1/3-ish of a mosquito. So we could just say 964 mosquitoes is our answer. So it turns out that over the 31 days, the rate of change of the number of mosquitoes told us that a lot of them were dying out, right? So we started out at 1,000 and we added the net change in the number and we lost 36. So that's what happened during the time frame from 0 to 31 days. And finally, part D. To the nearest whole number, what is the maximum number of mosquitoes for times t between 0 days and 31 days? Show the analysis that leads to your conclusion. So trying to figure out what was the maximum number of mosquitoes at a particular time on the island. What was the most amount there ever was? So we know how many mosquitoes there were on the island at time 0 to begin with. So this is a closed interval, so I would need to determine how many there were at time 0. Now here's the biggest mistake students are going to make is they're going to say that we're trying to maximize R. So they're going to say, well, we want R of 0, we want R of 31, and then any critical points. So set this R equal to 0 to find the critical points. But that's not the case. We're not trying to maximize R. So I'm going to erase this because this is completely wrong. So we're not trying to maximize R. R is the rate of change of mosquitoes per day. I want to maximize the mosquitoes per day. So I don't have the name of that function. So we're used to using that notation. We want to maximize f, so we set f prime equal to 0, etc. But we don't need that notation in order to figure out all the important days that we're going to need to check. So all we need to do is say that at t equals 0 days, there was 1,000 mosquitoes. And we even have how many mosquitoes there were at 31 days. We solved that in part C. So at 31 days, there was 964 mosquitoes. So right now, just checking the endpoints, we know that, or we could say that the current maximum would be 1,000 mosquitoes. But we need to check any critical points. So we need to check critical points by setting the derivative equal to 0. And again, for the who knows how many times, this is the derivative of the function that counts mosquitoes. So we don't know what that function is. We don't have a name for it, but the derivative of that function that counts the number of mosquitoes, the rate of change of the number of mosquitoes, is r of t. So I need to set this derivative equal to 0. So how we're going to do that, because we have a graphing calculator, so ultimately this is what we're trying to do, figure out when does r of t equal 0, between 0 and 31, we're going to graph it. And we already have it stored, so here's our y1. And before we graph it though, I'm going to go ahead and modify the window. So x min, so x in this case represented our t. And we only care about what's going on between t's between 0 and 31. So our x min will change to 0, and our x max will change to 31. Alright, so now our y min. So y being the output. So here, let's just go ahead and leave negative 10 to 10, because we're not entirely sure what this function maybe is necessarily going to look like. I mean, it has the cosine function in it. Just cosine itself goes from negative 1 to 1, but just to see, let's go ahead and graph this function. Alright, so we have a pretty good picture. We don't have the entire picture, but we do have where r of t equals 0 clearly shown. So there's two places where this function r of t equals 0, this derivative equals 0. So we have two critical points right about here and right about here. Now, normally we would have to check both critical points, but we are trying to find the maximum number. So I would say that the best thing to do is to eliminate any local minimum value, because that's not potentially ever going to be a maximum. So here this derivative graph changes from positive to negative, so that means the original function goes from increasing to decreasing, so this point here would be a local max. This is the one we want to keep and we care about. This other function, or this other critical point, is going to yield a local minimum, because this derivative graph changes from negative to positive, making the function change from decreasing to increasing, the original function, which means there'd be a local minimum. So we do not have to care about this point, only this one. Alright, so now I have to find this 0. So to review how to find zeros on our calculator exactly, because let me point one thing out. The trace option doesn't work. So here's what I absolutely cannot do, is just move my arrow over and get kind of close to that point and say, oh, that's the x value that I need. I absolutely cannot do that and will never ever work. So I have to go to second trace for calculate, 2 for 0, and now it's asking me for the left bound. So I want to be to the left side of this x-intercept right here. So I want to move to the left. So now I'm clearly to the left of this x-intercept. So I don't want to think about it as above or below the graph, the x-axis. I want to think about it to the left or to the right. So left bound, yes, so I hit enter. Right bound, now it's telling me get to the right side, which in this case would be down here. I'm on the right side of this x-intercept, so I hit enter. When it says guess, we always just hit enter. So now we have that this 0 is 7.85398, etc. Alright, so if we want to remember that value, we could go ahead and write it down. So 7.853. So let's just write it down so we remember it. But here is something that is crucial. I cannot just take this value, even if you go out to 25 decimal places or 25 places past the decimal, I cannot just take this numerical value and type it in right now when we set up our integral. I have to store this value. So right now the calculator is holding this number as your last answer. So what we're going to do, as soon as you see this value as the 0, I'm going to go to second and quit. I'm going to get to the home screen. And the first thing I'm going to do, I can't touch anything else, I have to hit STO for store. So what the calculator is doing is it's storing your last answer, which was, they're only saving the x coordinate. So the last answer, I want to store it to any letter in my calculator except x. I don't ever want to do that. but I want to store it to, let's say, A. So alpha A. So I'm using the green buttons on the back. If you have a different color calculator, it might be a different color. So alpha and then any letter you want. Usually we pick A, it's closest, and then we hit enter. And then we wrote it down so we remember. A is now 7.853, and it's the exact answer with all of the decimal places stored. So now I want to keep and hold that number. So that answer is in terms of days. Whoops, days. So potentially the maximum number of mosquitoes happens at 7.853 days. The only way we're going to know is to evaluate the integral from 0 to A. So what I'm going to do is, instead of calling this t now, I have labeled it as A. And on the AP exam, you're going to want to do this as well. So you're going to want to list what you stored as A, and then the integral we're setting up to find the number of mosquitoes there were at 7.853 days is the integral from 0 to A of r of t dt. So now we're going to go to Math 9 for integrals. 0 to my upper limit of integration is now A. So under no circumstances can you type in just 7.853 or even 7.853 blah 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 1020 places past the decimal. You have to put the stored value in. And then we can go ahead and choose the function y1 again, and then dx, and enter. And this number is going to represent the net change in the number of mosquitoes between 0 and 7.853 days. So this is the net change in mosquitoes between 0 and 31 days. So we can't forget to add, didn't leave much space for it, but we can't forget to add 1,000 to that net change. So that's how many mosquitoes were added to the island between 0 and 7.853 days. But there were already 1,000 to begin with, and our question's asking what's the maximum number there were. So the answer here is 1,039 mosquitoes. So the nearest whole number, we're rounding again, and that would be the maximum. So what is the maximum number of mosquitoes? 1,039 mosquitoes. This next problem has to do with particle motion, and we should think back to when we learned about the relationships between position, velocity, and acceleration. So just keep that in mind. A particle moves along a straight line. For times between 0 and 5, the velocity of the particle is given by this function here, and the position of a particle is given by s of t. So we just have to note we've been given the velocity function, and we're told what to call the position function. We're to call it s of t. It is known that s of 0 equals 10. So here, they've given us an initial position. So since s of t was the position of the particle, s of 0, so the position at 0, the initial position, is 10. So let's go ahead and see what the question is asking us to find. First, find all values of t in the interval from 2 to 4 for which the speed of the particle is 2. So this is actually a review question. The relationship between speed and velocity is that speed is the absolute value of velocity. So what we need to do is set up an equation that involves the absolute value of velocity. So this is like saying speed, and I want to know when does this equal 2. So when, at what times, when is the speed of the particle 2? Well, that's whenever the absolute value of v of t equals 2. So this function is one that we're going to want to enter into our graphing calculator. This whole problem is a graphing calculator problem. So we're going to go ahead and enter it, and I have actually already done that. So this is the function entered in as y1, and we can see that we only care about this between 0 and 5. So before I even waste any time graphing on the standard viewing window, I went to Window and changed my min and max on the x values, because this is in terms of x on my calculator, not t, and change that to 0 and 5. And for y min and y max, we'll just go ahead and start with negative 10 to 10 and hit graph and see what happens. So this is the graph of my velocity function between 0 and 5, and then negative 10 to 10. So we can see we can't see the complete graph. So one of the things we might try just to see if we can see any other difference is change my y-min value. Let's go ahead and make it negative 15 and see how that looks, if we can see any more detail about the graph or if it really just keeps going down forever. So we can see that the graph isn't at least going to do anything crazy between 0 and 5. So this is a pretty okay picture of velocity between 0 and 5. Now let's just try to make sense of what's happening. So if this is the velocity function, the velocity at 0 is right here at negative 2, and we can see that v of 0, sorry about that, we can see that if we were to substitute in 0 into t, well, 0 squared plus 3 times 0, this whole piece is 0, t cubed is 0, so we do get out negative t. So the initial velocity is negative 2. So let's keep in mind, we're not looking at the position function, right? So we're not up here at 10, this is a velocity function. So the initial velocity is negative. So what that means is, at the start, the object is traveling to the left, because velocity is negative below the x-axis. And then right here, when velocity touches the x-axis, well, the velocity is 0, which means the object is at rest. And then the velocity is positive on this region here. So velocity is positive, which means that the object is moving to the right. And then again, the velocity is 0 when I touch the x-axis, so I'm at rest, and then my object is traveling again to the left because velocity is negative. So I'm assuming left or right. It didn't tell us if this object is moving along a horizontal line or a vertical line, but just for the purposes of understanding what we mean by negative velocity and positive velocity in terms of direction, it's either going down or to the left here, up and to the right here, or down and to the left here. And at rest when I touch the x-axis. So just to get a general idea of what's happening to the particle. So now, when is the absolute value of velocity equal to 2? So I didn't graph the absolute value of velocity, I graphed velocity. But because this is a graphing calculator problem, what I can do is I'll just unhighlight y1, this was v, and go down to y2 and go to math, move over 1 for absolute value, and then recall, so go to vars, y-vars, y1. Now I'm going to graph the absolute value of y1. So we can see that what happened was we reflected the part below the x-axis to above the x-axis, and what we're interested in doing is knowing, well, when does this graph equal to? So what I have to actually go back and do is enter in the function 2 and find those points of intersection. So let's go ahead and do that. Whoops. So let's go ahead and enter y3 as, as 2. Graph that. And this is actually kind of a tricky problem because I need to find all values between 2 and 4. So that means I really only care about what's happening. That's 1. So right here is 2, and right here is 4. So I really only care about these two values here. So I'm going to go ahead and go to second, calc, 5 for intersect, and I'm on the first curve, and I'm going to hit enter. I'm still close to that point of intersection on the second curve. Enter, guess, hit enter. Alright, so we found that point of intersection was 3.127, or we could round to 3.128. So x equals 3.127, or 3.128. You don't have to write both values, either one. So that was one point of intersection, and then we have to go to second, calc, 5 for intersect, move ourselves over to the other point of intersection, again strictly between 2 and 4, so that's why we only care about these two. Enter, enter, enter. So 3.473, and even if we round it, it's still 3.473. So remember, we have to go to at least the thousandths place, 3 places past the decimal. So these are my two values, again, between 2 and 4. So that was kind of tricky. I have to pay attention to details because I could see I cross a couple times across the whole interval from 0 to 5, but this is really a test in how closely are we reading the instructions. So now let's go ahead and look at part B. Part B is asking us to write an expression involving an integral that gives the position s of t. So we were given the velocity function, and we have to write an expression involving an integral that gets us the position function. So s of t, the position, well, the position at any time, we first have to take into account where the object was to begin with. So s of t, to begin with, was at 10. So I'm going to label what we're doing here. This is my initial position. And then I have to take into account my change in position. Now that had a special word that we call displacement. And we've just recently learned that the integral of velocity is displacement. So we want the displacement from the initial position, the starting time, to whatever our ending time is. So I want to know the initial position plus this is the displacement, or the change in position, because that's going to tell me my final location, right? If we think about what's happening, we're saying, well, we started at 10 plus however much I change position, that's going to tell me where I'm at after t units of time. We weren't even given a unit of time here, but after t units of time, I would plug that t in right here, which creates a problem for having a t right here. So although we know that displacement is the integral of velocity, and we're used to velocities being in terms of t, because t is in my upper limit of integration, I need to put a dummy variable into the function v. So let's go ahead and change the color. So I need, let's say, v of x dx. So this is what represents my position at any time. So my total position is whatever my initial position was, plus my change in position from the time 0, the starting point, to whatever time I'm about to plug in right here. And now we're going to use this expression. So use this expression to find the position of the particle at time 5. So now, what's great about having this equation, this function, is that I can just substitute in different values. And at this time, I'm being asked to substitute in 5. So the integral from 0 to 5 of v of x dx is something that I can quite nicely plug into my calculator. So I've already stored v as y1. So I'm going to go ahead and enter 10 plus math 9 for integrals. And I'm going to integrate from 0 to 5, because remember, my calculator does definite integrals of, I've already stored this as y1. So s of 5 is, it's doing its calculation, negative 9.207. Negative 9.207. So after 5 units of time, again, we weren't given units in this problem. So after 5 units of time, where was my particle? Well, it's at negative 9. So it started at 10, and then it moved to the left. Again, let's just assume a horizontal line. Now, after 5 seconds, it's all the way at negative 9.207. So now let's go ahead and take a look at part C. For part C, we're asked, find all times t in the interval from 0 to 5, at which the particle changes direction. Justify your answer. So we actually talked about this when we analyzed our original graph. So we don't want the absolute value function anymore. We don't need the 2 function anymore. We're going to go back up and highlight only y1 and graph that. And we talked about how when velocity was negative, then the object was moving left or down, and when the velocity was positive, the object starts moving to the right or up. So when does this thing change direction? When velocity changes sign. So not when velocity equals 0. I'm going to find the zeros right now, but I could ultimately bounce off the graph. So it's not when velocity equals 0, it's when velocity changes sign. So changes from either negative to positive or from positive to negative. So I'm going to have to find these 2 zeros right now. So second calc, 2 for 0. And I'm going to have to move over here, get to the left of that 0. Whoops, lost my calculator. Oh, I guess it just really wants to stay over there, so we'll let it. So I need to get to the left, and then I need to get to the right of that 0. Enter, enter. Alright, so 0.536 is when velocity changed sign, so that's 1 time when this happens. So at, not x. So at t equals, so I guess this should have been a t too, whoops. At t equals 0.536. And then again, instead of going through all that process, I mean, ultimately we're going to have to go left, right, 0 again for this point. I'm just going to tell you what the value is. So the value is 3.317, or on this case, we could have rounded, so we could have put an 8 here. It's one or the other. So these are the two places where v of t changes sign. So we needed that justification that was asked for, and that's what the justification is. So those are the 2 times. And here's the justification, because v of t changes sign. So now let's go ahead and look at part D. We'll go ahead and do that over here since we're running out of space. Is the speed of the particle increasing or decreasing at time t equals 4? Give a reason for your answer. So this goes back to a topic when we reviewed velocity, position, velocity, and acceleration, that something is speeding up or the speed is increasing when velocity and acceleration have the same sign. So I'm hoping it's starting to come back to you after I just said it. So speed increasing or speed decreasing, we're looking for the sign of both velocity and acceleration at this particular time. So we need to analyze v of 4 and we need to analyze a of 4. But again, lucky for us, this is a calculator problem, so this isn't going to be too bad. We already have the function v stored. So v of 4 is y1 of 4. So I'm on my home screen, just plugging 4 into that velocity function. I get a negative value. So v of 4 is negative 11.475, which is less than 0. And then again, because I have my calculator, this is not a hard problem at all. I am not being asked to, although we totally could and you should be able to. We're not even asked to find the derivative of this, the acceleration, by hand. I can just go ahead and go to Math 8. We should really remember the shortcuts by now. And find the derivative with respect to x of y1 at that value 4. And we get another negative value. So we get negative 22.295, which is also less than 0. So v of 4 is negative, a of 4 is negative, so the particle speed is increasing. And the reason for our answer is already present, that v of 4 and a of 4 are both negative. So the speed of the particle is increasing because v of 4 and a of 4 have the same sign. So not a lot of this is really new. I mean, we're just going back over it for review because we can't forget anything. The only thing that's new that really ties into the net change idea is this piece right here. So we're talking about position, which is initial position, plus the change in position, which is an integral, as we were required to do and write an expression involving an integral. Alright, for parts E and F, I cleared the screen because we're going to need a little bit of space. And what I want you to know is that parts E and F were not original to this AP problem, so this whole thing through A through D was an exact AP problem. I've just gone ahead and added 2 parts to the question that are very common when given a velocity function. So you're going to see these quite a bit in addition to A through D. So instead of looking at a whole nother function, we'll just answer these to do with this particular velocity graph. So I'm assuming in my part E that this was along a horizontal line. So in my part E, I'm asking, when is the particle farthest to the left? So we've talked about this. Farthest to the left means that we're trying to find an absolute minimum. And this is important because we're talking about farthest to the left. It's an absolute minimum of position, of s of t. So I want to know, when is the position function going to spit out the most negative value? Because if I'm thinking about a horizontal line, if I'm furthest to the left-hand side, that's where more negative numbers live, right? If I'm thinking about horizontal, like the x-axis. So I want to know, when am I absolutely the smallest value, the minimum of the position function? So to find an absolute minimum, we're going to have to check the endpoints and the critical points in S of t. So the endpoints, we had to reference the original problem statement. We only cared about what's going on between 0 and 5. So that means we have to check, this is part E, we have to check S of 0 and we have to check S of 5. And then we have to check critical points. So remember, critical points are where the derivative, well, the derivative of position is velocity. Where does v of t equal 0? And we have already, in fact, found these two values. We found these two values in part C. So we found, and we rounded these, 0.536 and 3.317. So if we really wanted to, we could check both of these values, but we, in fact, only need to check one. So if we go back and we analyze the graph of v of t, the two values, 0.536 and 3.317, only one of those has the potential to be an absolute minimum. Because we have the velocity graph, we have the ability to determine whether or not these critical points are local maximums or local minimums. So this first critical point, 0.536, velocity changes from below the x-axis to above the x-axis, or velocity changes from negative to positive. So that means that the position function changes from decreasing to increasing. And if my position changes from decreasing to increasing, that makes this value here a local min, local or relative. And 3.317, if we go back and look at what happens there, velocity changes from positive to negative. So the original function, position, changes from increasing to decreasing, which makes this a local max. So if I'm trying to find an absolute minimum, there's no way a local max, right, a peak in the graph, can be a minimum value. So I don't even have to bother with this point. I only have to check the position function, S, at 0.536. But I'm going to have like a little asterisk there. I cannot, and I repeat, cannot plug 0.536 into the position function that I have just like that. That means that I have rounded at an intermediate step, and I'm not allowed to do that. So what I have to do, and you'll see that I've already done it, is you have to store that value. So back when we found this 0, going through that process on the graph, I stored it, I stored my answer to A. So 0.536033154, etc. has been stored under A, and that's the value that I have to use when plugging into S of t. And let's remind ourselves, we found S of t in part B. So S of t was the integral from 10 plus, the integral from 0 to t of v of x dx. We needed that dummy variable. So this is my position function that I'm about to plug my endpoints and critical point into. And you'll notice if I plug in 0, it's the first thing I need to do. Well, the integral from 0 to 0 is just 0. So the answer is just 10. But we didn't even need to do that because I know S of 0 equals 10. So that's the first value. S of 5, we actually don't even need to do that because we'd be doing it again. We found that in part B. So that was negative 9.207. And then S of 0.536, again, we would have to do that. We would have to do 10 plus math 9, the integral from 0 to alpha a. So remember, I stored it. I cannot put 0.536. And then vars, y1, and then an x. So I get 9.402. Alright, so when is the particle farthest to the left? Justify. Well, justify is all this work that I've shown. So when is the object furthest to the left? Well, that happens at t equals 5. So I can see the absolute minimum is negative 9.207. 0.007. But that's not what the question was asking. The question was asking, when is the particle farthest to the left? So the answer is the time. So at t equals 5, the particle is farthest to the left. So I'd have to write this out because it's the understanding that you're answering the question, right? We're not just memorizing, oh, plug in endpoints, plug in critical points, okay, circle this is the answer. So if the question asked, where is the particle when the particle is farthest to the left, then my answer is the y value. But it's asking when is the particle farthest to the left. So that means that's the input, that's the time. And now finally, we'll look at part F. Part F is asking, what is the greatest distance between the particle and the origin during the time interval from 0 to 5? Show all work that leads to your answer. So this is a matter of, we really should be able to think about what's happening on the straight line. So again, we were assuming horizontal. So what's happening over the course of 0 to 5 seconds is, let's go ahead and change color. So this is my horizontal line. At time 0, the particle was at 10. So let's go ahead and say at 10, I start at t equals 0. And then what happened was, again, we analyzed the graph. We said, well, the particle started heading to the left because velocity was negative. So the particle started heading to the left, and it got all the way to 9.402. I guess that's not very far. 9.402 after 0.536 seconds, right? So that's what's happening. So it gets right here after t equals 0.536 seconds. And then, if we look at the graph, for all of this area, because that's the displacement, between 0.536 and 3.317, my object starts moving to the right again. So my object starts moving all the way to the right some amount. Well, if I want to find out exactly where my object's at 3.317, now for part F, I'm going to have to check that value. So S of 3.317, which means I'd have to go back and store that because, again, I can't just plug in the rounded value. But you'll notice I already did store it as B. So I'm going to go back and change this to alpha B. Enter. And I'm at 20.038. 20.038. So I'm all the way over here. So that's not infinity. Let's just say this is 20.038. That's where I was when I stopped at 3.317. And then what happens? Let's see. If I analyze the graph again, well, then I go all this negative area to the left because my velocity is negative. And at the very end, where am I at? Well, at S of 5, I'm all the way over here at negative 0.9. I don't know why I keep saying 0.9. At negative 9.207. So after 3.317 seconds, or units of time, because we don't have a time, I turn around, go to the left, and right here, this is where I end up at 5. Alright, so I've figured out, I've mapped, and not that you'd have to show this graph, but I really think you should be able to. This is the motion of the particle along the straight line. So highlighting all of its important attributes, all of its important pieces of switching directions. So started at 10, went to the left for a little bit, for 0.5-ish seconds, and I stopped. Then I turned around, headed to the right up until 3.317 seconds, stopped at 20.035, and then headed all the way to the left to negative 9.207. So, my question asks, what is the greatest distance between the particle and the origin? Right? So the origin meaning 0. So, what is the greatest distance? What was the farthest I ever was away from the origin? So in this case, it's 20.035 as the answer. Now I want you to keep in mind, they probably would not ask parts E and F together. Again, I've just added these two parts so you can see how to do all these different types of questions to do with a velocity function. So you would actually have to show that you checked all the different places where you stop, turn around, and go back and forth. So you would actually have to show s of 0, s of 5, and s of 0.536 again, but it wouldn't be again because it's not like you would have just done part E. So just to show you the work that would have been involved is you would have had to write all this out. 9.402. So this is that show all work that leads to your answer. So it is, again, checking, well, where is this thing at all those important moments in time, the endpoints and those critical points where I change directions. And then once I figure out all those locations, well, what's the farthest location from the origin being 0. So if I'm all the way at 20.038, I'm 20 units away, so that's the farthest I am.